Good afternoon, pilot teachers, and good afternoon, students.
Good afternoon.
Thank you. Sit down. We're still looking at information on plate movement. And Gideon asked me yesterday, Miss, I did not really understand what we were looking at yesterday. So I'll go through the introduction of that lesson again, and then we'll move on to what I'd like us to look at for our lesson today. Okay, if you can maybe focus on what we covered yesterday. We covered two things. We looked at the convergence of plates. And from the convergence of plates, we looked at the process of subduction. And as well as that, we looked at fold mountains, which are a feature that is created as a result of convergence of plates. And that is what we looked at in our lesson yesterday. Then you were supposed to construct three-dimensional diagrams, and those diagrams were supposed to show the stages in the development of the feature, which is a fold mountain. We looked at those features in reality, and we referred to the converging of the oceanic plate, which is the Pacific plate, converging or meeting or colliding with the South American plate. And when two plates converge or when they come together, there are certain features that are created. Those features are, a trench would usually be formed when an oceanic plate meets up with a continental plate, or an oceanic plate meeting up with another oceanic plate. And usually, the lighter of the plates would subduct. So in subduction, it is simply the process whereby the lighter plate is actually forced beneath the other plate, which is going to be a little bit more heavier or denser. And that's what we looked at. We also looked at fold mountains. And fold mountains around the world are generally formed as a result of the converging of plates. And where you have an oceanic plate meeting another oceanic plate, you will not find fold mountains. It is usually when an oceanic plate meet up with a continental plate, and then on the continental plate, the land tends to buckle, and the buckling of the land as a result of the converging of those plates will create the fold mountains. You can also have fold mountains forming when a continental plate meets another continental plate, and the land area in between is actually forced up. In the case of the Himalayas, that is another example. But yesterday, we concentrated mainly on the formation of the Andes. That's what you were supposed to make note of in your lesson yesterday. So let's check. Is there anyone who has any questions or queries now that you'd like to ask with regards to what we looked at yesterday? The information from the handout that was distributed were your background reading. So if you had read on, you would have understood a little bit more on maybe the stages in the development of the fold mountains of the Andes of South America, and also the process of subduction. Okay, if there are no questions, we'll continue on with the information that I'd like us to look at, and that is on, we're still on looking at the movement of plates, and we're still looking at plates converging. Yesterday, we looked at an oceanic plate meeting a continental plate. Today, we are going to look at an oceanic plate meeting another oceanic plate, and the features which are formed as a result of the convergence of the plates. So it's still on convergence, oceanic plate meeting another oceanic plate today. You have a handout which is given. We're going to make reference to that handout, and at the same time, the diagrams from that handout to be explained on the monitor. Two words we looked at yesterday that I'd like you also to make reference to. The definition to what subduction is, that is what we have covered already, and also the definition to the Benioff zone, which I explained, that is simply a seismic zone whereby earthquake focus is actually or usually shallow near the base of the ocean trench, and then the earthquake focus gets to intensify or increases as we move towards the deeper part where the plate subducts. And I'll explain that a little bit more when we go on to the information on ocean to ocean convergence today. So our lesson today will be basically looking at some of the features that are formed as a result of an oceanic plate meeting up with another oceanic plate, and you will also be expected to explain in your own words how one of those features is actually formed as a result of that movement. And that is going to be for the formation of what we call Volcanic Island Arc. I'll come to that when we come to that activity. Okay, we're making reference now to the information from our readings, and every one of you should have a copy of the handout. And I'd like us to look at the information from the handout. We note in convergence, I already mentioned that when plates converge, we can have a continental plate meeting a continental plate. You can have an oceanic plate meeting a continental plate. And today we will concentrate mainly on an oceanic plate meeting another oceanic plate. So if we look at the diagram generally here on the board and also from the handouts you were given, the diagram on a monitor, sorry, you can generally see that these are some of the features that are going to be created when you have an oceanic plate converging with another oceanic plate. Some of the features are: ocean trench is formed actually where the subduction occurs. We already know what subduction is. The sinking of the lighter of the oceanic plate under the denser oceanic plate. Okay, so the subduction occurs. Upon subduction, you now have what we call the Benioff zone of earthquakes, and the triangles that are actually shown on the diagram represents the focus of the earthquake or the origins of the earthquake as the plate tends to subduct further and further down into the mantle. Meanwhile, on the surface, we have the trench being created or formed. You also have what we call the accretionary wedge, which is this section of the landform on the surface that is formed as a result of the subduction of a plate. Then we also have this section or this area here that is formed, which is known as the Forearc Basin, which is created as a result of that movement. You also have a line of islands which are referred to as Volcanic Island Arc. If they are of volcanic origin, then they are referred to as Volcanic Island Arc. And if they are not of any volcanic origin, then they are generally referred to as the Island Arc. But usually, most of them tend to be of volcanic origin. Therefore, we refer to them as Volcanic Island Arc. It's just like the islands of Karkar, Manam, Bagabag, and etc. That's a line of islands been formed. They are volcanic islands. If we really look at them on the map of Papua New Guinea, we can see that they tend to follow a line. Similarly, the Volcanic Island Arc formed in that manner when an oceanic plate meets up with another oceanic plate. You can see from our diagram here, there is absence of fold mountain. From our lesson yesterday, we did see fold mountains because there was a continental plate meeting with another oceanic plate. But today, there is absence of fold mountain because of the nature or the type of plates that is moving is basically ocean to oceanic plate, motion converging, coming together. So we are going to look at now a little bit of information surrounding some of those features and how they are created as a result of that movement. Okay, we'll go over to the information from our handout. Note, when two plates kept by seafloor converge, one plate subducts under the other, as is the case of the example of the Pacific plate sliding under the western Aleutian Islands. The Aleutian Islands, if you look at generally the world map, you will find them in the Pacific area, very close to North America or Alaska, that is, and also Asia or Russia. But in the Pacific area, there's a group of islands which are known as the Aleutian Islands, and that's where they are located. The subducting plate bends downward, forming the outer wall of an oceanic trench, which usually forms a broad curve convex to the subducting plate. When we talk about convex, that is simply a slope that goes out or in? Out. Okay, a slope that goes out is convex. A slope that goes in is concave. Double check on that. Double check on that to see whether we've agreed with the definition of convex and concave. A slope that goes out is convex, and a slope that goes in, that is concave. Okay, now let's go on to looking at that information with the illustration also from our handout and information from that monitor. If we had a ping pong ball, we're imagining ping pong ball, that's a table tennis ball. It's not the tennis ball, the lawn tennis you play, but the table tennis. Okay, we get the table tennis ball or ping pong ball that is, and you rule or you draw a small square on it similar to the information as shown here. And then you put an arrow after you've drawn that particular area to show a plate or to represent a plate. Then you put in that arrow there to show the movement of that plate. Okay? What you would do then is you slightly maybe press or dent onto where the square that you have drawn with the arrow. And then what you will see is actually a bend where the arrow you've drawn will be formed. And when that bend is actually formed, or the dent in the ball will create that bend in that arrow that you've constructed, that then will represent or can represent a trench with a convex shape or slope, representing how a trench would actually look like or be formed in reality when it is subducting, or how a trench will be formed in reality when an oceanic plate is subducting. And that is also the reason for why you can say, the dented ping pong ball can show why trenches are actually curved when you look at them in reality. We move on. It also tells us that as one plate subducts under another, a Benioff zone of shallow to intermediate and deep focus earthquakes is created within the upper portion of the downgoing lithosphere. So if we go back to the diagram, we can see that as shown by the star, or as represented by the star. It goes on to say that the existence of deep focus earthquakes to a depth of about 670 kilometers tells us that the brittle plates continue to that depth. So if a plate is actually subducting, and if we find out that the earthquake is down to about 670 kilometers from where subduction has originally taken place, then we can say that the brittle plate is still being carried further down with it. Because this is one way in which we can tell how far down a plate is actually subducting or going down. Some subduction may be shallow, some subduction may be deep, and they continue on to go for as far as about 670 kilometers, as given here with an example. It also tells us that the pattern of quakes shows that the angle of subduction changes with depth, usually becoming steeper. Some plates, they crumple or break into segments as they descend. So sometimes the plates get to crumple or they break as they are actually descending. Other times, whatever is carried with it down in the process of subduction continues on to be carried further and further down into the mantle until it melts, it forms the material within the mantle, and then the convection currents will bring them up again, and the cycle continues. The descending plate somehow generates andesitic magma when it reaches a depth of 100 kilometers. So we come back to this diagram here. This point here is important. By the time the subducting plate reaches a depth of about 100 kilometers, around this area here we're looking at 100 kilometers, there is actually what we call andesitic magma which generates within the mantle. So the descending plate somehow will generate that endostatic magma when it actually reaches depth of 100 kilometers. A likely source for the andesite is the partial melting of the asthenosphere just above the subduction zone. And it is reckoned that perhaps that particular process is triggered by the dewatering of the oceanic crust as it is descending or as it descends. We've looked at differentiation and assimilation. That is to do with the settling of the heavier materials towards the center and the lighter materials out towards the outer layer of the earth. And it says there that differentiation and assimilation may also help form the endostatic magma. Maybe you might be wondering, why is this particular information important? It is going to be important because when we look at the formation now of the volcanic arc, this is where the material is actually coming from to make those volcanic or those islands referred to as volcanic islands or volcanic arcs. They cannot be of volcanic origin if there is no magma coming up to them and then being released as volcanoes. So it's important we need to note where that magma is actually coming from. It tells us there in the next paragraph, however, the endostatic forms, or however that particular magma is actually formed, it works its way upwards through the process of the convection currents. And when it works its way upwards, it might come out to the surface and then it will erupt. And as that magma comes out to the surface and it erupts, then it will form island arc or island arcs. A curved line of volcanoes that form a string of islands are referred to as island arcs. And they are usually parallel to the oceanic trench. And we all should know how an oceanic trench would actually be formed. So if you look at how they are formed parallel to the oceanic trench. And these particular islands are formed as a result of the subducting of plate until about 100 kilometers deep, where the magma is regenerated and is actually created, and the convection currents within the mantle will make that magma rise up to the surface, and upon rising, it will erupt, and upon eruption, it can form a line or a chain of islands. Another important point that we need to make reference to also is the distance between those island arcs when they are formed and the trench can vary. So the distance, that means between the trench and the island, the distance here can actually vary. And what would actually contribute to the variation? We read on, it says, it will depend upon the subducting plate reaching the 100-kilometer depth. If the subduction angle is steep, then the plate reaches the magma generating depth at a location close to the trench. So the horizontal distance between the island arcs and the trench is actually short. Okay, so if you look at the example here, if the subduction is actually steep, then the distance between the trench and the island arc is going to be short. So the distance here. If the subduction is actually steep, the distance between the trench and the island arc is going to be short. So from the information on the monitor, it says there that the endostatic magma is generated where the top of the subducting lithosphere reaches a depth of about 100 kilometers. So the subduction angle will determine the arc trench spacing. We move on. If the subduction angle is gentle, the arc trench distance is going to be greater. Here, it tells us that the endostatic magma is generated where the top of the subducting lithosphere reaches a depth of 100 kilometers. So the subduction angle determines the arc trench spacing again. So if you look at the subduction here in comparison to the first one, the first subduction here is steeper. Therefore, the spacing is shorter or smaller. Then if we look at the second diagram, you see the subduction is a little bit more gentler. Therefore, by the time that particular subducted material reaches 100 kilometers, that's where the rising of magma comes to the top now, resulting in formation of the island arcs. But then the distance between the trench and the island arc would be a little bit more further as compared to the first one where the subduction was steeper. We're following. Finally, it goes on to say there, a thick, buoyant plate may subduct at such a gentle angle that it merely slides horizontally along under another plate. And since the top of the subducting plate never reaches the 100-kilometer depth, such very shallow subduction zones lack volcanism. So if we look at the third example, no arc, no volcanic islands. Why? The subduction process was very shallow, that it was so shallow that that particular material never reached the 100-kilometer depth for the generating of magma in that area to reach the surface to form the island arc. So here we're looking at andesitic magma is generated where the top of the subducting lithosphere reaches a depth of 100 kilometers. Therefore, or so, the subduction angle will determine the arc trench spacing or no arc at all. And if the process of subduction is so shallow, then here you can see no volcanic island arc will actually be formed. The rest of the information I would like you to read for your background information or for your homework. Let's do some activities. Into your exercise book now, I would like you to actually explain how volcanic island arcs are formed. You explain in your own words how volcanic island arcs are formed. And if you'd like to use diagrams to help you with the explanation, you can go ahead to constructing diagrams to help you with the explanation. It's this particular depth that we are looking at. So in other words, we are saying that about 100, as we go about 100 kilometers down, that's where the regeneration of magma is. So that's the area where we expect to find, like if you had a volcano, a magma chamber, this is where you expect to find it about 100 kilometers down. And if it is a conduit which connects the chamber to the mountain at the top, then you can expect continuous lava flow from that particular magma chamber up the conduit to the volcano. But if maybe a volcano is there, but maybe the conduit does not go down to about 100 kilometers where the magma is likely to regenerate there, then the volcano once in a while might have
magma coming out onto the surface or lava flow, because maybe once in a while, due to tectonic movements, magma may actually be forced to be under that particular volcano, resulting in it rising and then magma flowing out. Okay, so what they are saying generally is that as you go to about 100 kilometers down, you would expect the regeneration of magma, resulting in magma being, flowing like in a mobile zone or asthenosphere, that is. And it is within that area, as soon as a plate subducts, it will create, or it will allow for the magma to actually come up onto the surface where the two plates are converging, resulting in the formation of volcanic arcs.
So that's from here to here, that's 100 kilometers.
It should be approximately. We are not saying exactly. In some areas, it might be shorter, depending on the activity taking place under the surface in certain spots. There are some spots around the world which are referred to as hot spots. And in those hot spots, you can find isolated volcanoes where you don't expect volcanoes to be. I'll give you a good example. If you look at the Pacific Ring of Fire, where is your map of the world? You have a world map showing us the plate tectonics or plate boundaries? One of those maps that maybe we looked at already. Yeah, this one here, you see. If you look very carefully at the second diagram here, it shows us the distribution of earthquakes. Obviously, if there are earthquakes, we can expect to also find volcanoes. You look at where the location of Hawaii is. Where is Hawaii located? It would be here, somewhere in the Pacific. But Hawaii is also a chain of volcanic islands. Those then are all over plate, and that's what we owe it to hotspots. But those hotspots are created as a result of that 100-kilometer magma, which is closer to the surface, and the crust being brittle, allowing magma to come up. Okay. So what we are saying is generally about 100 kilometers, you would expect magma to rise, forming. Were you able to pick up now from yesterday? Okay. More information. what you have written. Volcanic Island Arc are formed when a continental plate meets an oceanic plate? No. Oh, definitely yes, you can have a volcanic island arc being formed there where a continental plate meets an oceanic plate. But in the case of what we're looking at a continental oceanic plate meeting another oceanic plate. So make the correction here just for what we are looking at on our lesson today. So it's a oceanic plate meeting an oceanic plate. So correct this one here. This one. Oceanic. Oceanic. No, leave that. Leave it. Leave that. Oh, okay. Or an oceanic plate meeting. Okay, that's fine. The lighter oceanic plate subducts and goes underneath as it reaches a depth of 100 kilometers. Hot magma makes its way up to the surface to erupt as island. Okay, so define. What do you think are island arcs? Your explanation is good as it is. So now I'd like you to define. What do you think are island arcs?
Okay, there are a couple of students who have actually finished with that work, and I'll get at least 2 students to read out what they have written. And for the rest of you, you're going to make sure that that work is completed for your homework. The explanation of how a volcanic arc is actually formed. Mason, we'll get Mason to read out what he's written on explaining how a volcanic island is actually, or a volcanic arc, sorry, not a volcanic island, but a volcanic island arc is actually formed. Meanwhile, the rest of you, you need to check on your explanation and ensure that any information that is going to be mentioned and you might miss out, you can include to your explanation on how volcanic arcs are formed.
Volcanic arcs are formed when the subducting plate, an oceanic plate, converges with a continental plate or another oceanic plate, reaches a depth of 100 kilometers deep. The descending plate somehow generates endostatic magma when reaching the asthenosphere, which is aided by the convection currents and flow to the surface of the ocean floor, forming volcanic arcs.
Okay, so very good. If you listen very carefully to his explanation, he's talked about subduction. He's also talked about the depth of which the plate must reach for the magma to actually come to the surface to form a line of volcanoes or an island arc. And that's important. Make sure in your definition that is also included. Would someone like to tell the class what they think is the definition of an island arc? What are or what is an island arc? Gideon, can you explain to the class what you think is a volcanic island arc?
Volcanic island arcs are formed as a result of 2 oceanic plates converging. The lighter, less dense plate is subducted under the heavier, more dense plate. Therefore, when the subducted plate reaches a depth of 100 kilometers, it causes the generation of magma to be forced up out of the overlying plate. This eruption of magmatic rock then cools off to form island arcs. Because these island arcs are formed as a result of volcanism, they are said to be volcanic island arcs.
Okay, good, very good. He is explaining again how volcanic island arcs are formed. Well done, good explanation. I think that is also very clear and straightforward. Now we come back to looking at island arcs. What are they? Simply, they are supposed to be a chain or a line of volcanic mountain peaks reaching out onto the surface from under the oceans of water. They're supposed to be islands. You see, Karkar is an island, right? It is also a volcanic island. Manam is an island. It is also a volcanic island. Bagabag is an island. It is a volcanic island. If they form a chain or a line, then they form what we call volcanic island arc, or arcs, yes. That's what volcanic arcs are. But from the 2 explanations, I think you have and you know how to answer this particular question. The rest of you ensure your answers are in your exercise book, and that will also bring us to the end of our lesson. If you can stand up now, class. To the pilot teacher, our keyword for lesson 27 is arc. Good afternoon and thank you, students.